In this video, we will go into the fundamentals of how large language models perform text generation. Let's take an example using GPT-2. We provide an input prompt, Mary had a little lamb, and our expectation is it will produce an output string such as its fleece was white as the snow. At this point, we can think GPT-2 as a simple function that takes an input string and produces an output string. However, in reality, this doesn't happen as such. Instead, when you give an input prompt, GPT-2 will only produce a single token. In order to get the next token, we have to append the generated token back into the prompt and call GPT-2 again. This will give you the next token. So we keep doing that until the desired number of tokens are generated, or a special token that indicates the end of token generation is produced by the model. Let's take a look at how the single token was generated. GPT-2 assigns probabilities for each token in the vocabulary based on what it has seen so far. What do we mean by this? So if we input the Mary had a little lamb prompt into GPT, it will produce a table or a matrix. And this is a busy one, so let's break it down. So on columns, what we have are the possible tokens that GPT-2 can produce. This is what we call as the vocabulary. So for example, think of them as words in the English language. In our example, we have 50,257 possible tokens that the model can output, and those we indicate in columns. The rows correspond to the input tokens in the input prompt. Here we have Mary had a little lamb, and I'm loosely corresponding a single word as a single token. Depending on the tokenizer you use for a model, it may be different, but for the sake of example, let's say that Mary is a single token, had is a single token, A is a single token, and so forth. So in order to understand what this matrix tells us, let's only look at the last row. This corresponds to the last token in the input prompt. So what it tells us is that if the model has seen all the tokens, including and up to the last one, then this row assigns probabilities for all the tokens in the vocabulary so that we can sample from it and produce a single token that will be the most likely one to come as the next token. Now that we have some idea about how GPT-2 works overall, let's try to see internally what goes on. And before we jump into the details, let's try to get some insights into how we want this inference to be. So let's take a goal. The first goal is, given a word, is there a way for me to find another similar word? For example, if you are given the word lamb and if you are given the dictionary of possible words, is there a way for me to find a similar word to this lamb word? Now, one way to think about it is, if lamb was not a word but a number and all the other tokens or words I can produce are also numbers, then it's quite easy for me. Then all you have to do is find the number that is closest to the word lamb. Now instead, what if lamb was represented as a vector? And all the other tokens are also represented as vectors. So lamb in this case is a series of numbers, and all your other words like goat, cat are also a series of numbers or vectors. Now in this case, we can use cosine similarity or vector dot product. So if you take the word lamb and take the dot product with the word token, let's say goat, and if you take the dot product with cat, you might end up with something like this. So it may say lamb and goat has a higher similarity than lamb and cat as just two words. So this gives us a mechanism to find, given a token, that I have a mechanism to find a similar token out of my dictionary by taking the cosine similarity. Now let's set another goal. I'm not particularly interested in finding a similar word to a given word. What I'm interested in is finding the word that is most likely the one to come next after a given word. So in order to do that, let's see if we can change this given word lamb into something else, so that if we take the similarity with that something else, we will find a word which is the one that's most likely to come after lamb. So for example, if you were to take this lamb and also represent the position where it was in the sentence, and so that we can get some context captured, and transform it. We change it to some other word like lamb prime, and then we try to find a similar word to this lamb prime out of our dictionary. So in that case, let's say this lamb prime was similar to the word eats more than it was similar to the word goat. Now, by doing this transformation, what we have done is we are still finding a similar word to this transformed one, but now that similar word we find is the one that is most likely to come after the original word lamb. So this is the idea of a transformer. The mechanism to find a similar word is still the same. It is cosine similarity using vector dot products. But what we have done is, instead of just finding the similarity between the original word and a bunch of words in the dictionary, we have changed the original word based on the context that it was in to a different shape, so that now when we take the similarity of that different thing, we will get a word that's the one that would most likely come after the original word. With that, let's dive into the mechanics of GPT-2 inference. So how does the inference flow look like now? So we have an original prompt coming from the user, and for all the words, we need to encode them into vectors. So which we will do, and we will call them token IDs. Now token IDs refers to where in that dictionary of ours we can find these words. For example, Mary is the 24,119th word in the dictionary, and if you go into our dictionary, which we call as an embedding table, we will find the vector representation for Mary. Similarly, had is the 550th token in our dictionary, and if you look up in that 550th position in the dictionary, you will find the vector representation for the word had. So we have the same number of tokens as the original prompt when we encode. Now what we can do is, like we saw in the last slide, we can extract the token embeddings or the vector representations for these tokens. Now remember, we needed some context where they were. So that we can have a similar representation for positions, and we call that the position embeddings. So each position is now represented as another vector. So based on this, we can combine position and the token embeddings together to form what we call as this X matrix. So what does this X matrix look like? So we had 5 tokens all together, and each token, for example, the first token was this one, and then let's take the pen. So the first token was this one, and the first position embedding is this one. So we can combine those two and then produce this first row or first vector representation for the first token. Similarly, the second one was the 550th one, so we can take that, we can add with the position embedding and create the next row. So likewise, now we have created a matrix which has the sequence length or the number of tokens that was in the original prompt times the hidden dimension or the embedding dimension. Now we call this X. Now once you have this X matrix, what GPT-2 does is for inference is it sends it through a series of transformations. Each step is called a transformer, and these are individual or independent steps. You chain them through, and you end up with something called X prime. And at the end of X prime, you can do a layer norm, you get another X double prime. And from this X double prime is what we do this similarity computation that we saw in the last slide. So this is our changed word, or the tokens have now been changed or transformed. Now at that point, we look at these transformed tokens and try to find similarity with our dictionary so that we get this probability assignment for all the tokens in the dictionary. Now for example, if you look at this last row, like we just discussed in a previous slide, it tells us that, okay, if you have seen all the tokens up to and including the last one, then in this row you can find the probabilities for anything in the dictionary, and you can sample, let's say if you were to pick the highest one, maybe it is this one, this token might be the most likely one that would come after the last word, which was lamb. That's the idea. Now with that, let's go into the transformer and see how it works. So remember, the goal is to transform the original input tokens to something else. So we have these tokens, which are now coming with both the token embeddings and also with position embeddings. So we will send them through a layer norm step, followed by the attention step, which I'll come to in a minute. And then we will have a residual add, and then we get this matrix, we call that the XR. Then it goes through another layer norm, a bunch of up and down feed forward networks, and then another residual add, and then finally you get a transformed set of tokens. So you originally started, these were your tokens. So these were your original tokens with the position embeddings added. So this was Mary, this was lamb, and they got now transformed to something else. So what was the role in attention? Remember, transformers, what they do is they will take a token and make that token look like their peers. In a single sentence, that's what they do. And how do they do it? They use attention. Attention tells you a given token, how similar is it to other tokens. So using this score or using this similarity, transformers will transform a token to look like their peers. In the last slide, we saw the different things inside a transformer. So it had a layer norm, an attention layer, followed by another layer norm and a bunch of feed forward networks, and then you get the transformed output. So remember, the goal of the transformer was to take in a token and then transform it to something else, so that when you take a similar token to that something else, that similar token would be the one that's most likely to come after the original token. So that's the goal of the transformer. And if you take these components, these different things that was in a transformer, the key thing that does this transformation or helps with the transformation is attention. So now let's go and see how this attention works. So for that, let's take the same example that we had, the X matrix, where we had these original tokens coming in. So for example, we had this first token, which was Mary, and this one was the little token, and this last one was the lamb. Now what we do is we will take a token. Let's take this token little, and for that token we generate 3 new tokens out of the same thing. So we take this yellow and we generated something called a Q, we generated something called a K, and we generated something called a value. So you can think of these 3 things as 3 facets of the same thing, or 3 sides of the same thing. It's like if you have a person, you have 3 characteristics of the same person. So this is the same token, let's say this was the same little token, but now we created 3 different shapes for that. So how do we actually come up with this one? So the original token, if you take this token little, it was a 1 by 768. So one token was represented as a vector of 768. Now if you take that, so one way you can think about is you had a 1 by 768 token or a vector. Now if you multiply that with a matrix of 768 times 768, you get another 1 by 768. So this is, and these in 768 by 768 matrix you can call another weight matrix, which has already been trained. So by multiplying with this trained weight matrix, what you do is you create another representation for the same token. So you created not just one, you just created 3 representations. And one of them is called the query, the other one is called the key, and the other one is called the value. Now why do we call these query, key and value? This will be explained in a little bit, but just to give an idea, what we are trying to do in attention is to compare. So we want to compare tokens with each other. So instead of just going and comparing tokens directly, we are going to take these 3 sides So remember now the way we can think of a token as, we can think of a three-sided shape. So it had a query side, it had a key side, and on the back it has the value side. So when you want to compare a token with another token, what we do is we take the query side of the token that we are interested in comparing, and we compare it with the key side of other tokens. So if this is, let's say, this is another token and it had the same Q, K, and there's a different V for that one. So if I'm interested in comparing this token, I'll take this Q side and I'll compare it with the key side of others. So I'm going to take my query side and then I'm going to compare it with the key side of others. So in order to figure out how similar I am to someone else, I always compare my query side with the key side of others. Now what about this value side? So remember, in transformers the idea is you take a token and then you transform it to something else. So for each token you need to create a different representation at the end of the day, or like a changed shape or a transformed shape. And in attention, when we want to find this changed shape, we use the value side. So now if I know how similar I am to others, and if I'm trying to create or like project a new value for me, what I'm going to do is do some computation which will come into a minute, but for that we will use our value sides. So that's why we created this Q, K, and V. So instead of just comparing the vector for a token, like this little token, the yellow vector itself, with others, we created three sides and use them appropriately when we are comparing, and also when we are trying to project a new value. So let's go into a little bit more details now. So this is for a single token. Now let's do it for all the other tokens as well. So we created queries, query matrices, K matrices, and then the V matrix. All right. Let's take that simple or the single Q vector again one more time. So what we are interested in now is to see how similar this one is to others. So you can take Q and compare it with other K values. So how do we compare? How do we find the similarity between two tokens? The same mechanism. We had a mechanism where we take the dot product. So vector dot product will give us a similarity. So we are going to use the same technique. Now for the yellow token we had, we will take the blue side or the query side, and then we will try to compare, or we will try to take the dot product with all of the green sides of other tokens. That's what we do. And this will give me a set of similarities. So how similar this yellow token is to others. Instead of directly comparing the yellow with others, we compare the query side with key side, but that again is giving you a similarity. So all it tells is how similar is this yellow token to others. Now with those similarity scores, or what we call as the attention scores, found by using this dot product, a series of dot products, you can run it through softmax and then get them all like probabilities or weights that add up to 1. Now once you have that, remember the next step is to project a new value for myself. So for the same yellow token that we had, we want a different representation at the end of the day. So how do we find this different representation? So now remember, after finding this similarity, what I have is a set of weights or set of values that tells how similar is this yellow to others. This is the attention score vector. So for example, we were looking at this token of, let's say this token was the little token, and now this one tells me, okay, how similar is so here this is how similar is little with little, and this one is telling me how similar little with the token A. So likewise, so these are just telling me how similar things are with the previous tokens. Now if I have this information, can I use it in order to project a new value? Yes, you can. So there's a little thing that you can do, which is, let's try to clean up this one for a minute and then go back here. So what you can do is you can take these similarities, so the attention scores, and then use them in a weighted sum. Very similar to how a linear layer or a perceptron would work. So what we do now is we take our value vectors. So each token, remember, they had a value side to them. So we take the value side of each token and then we do a weighted sum based on this similarity score, and then we project that output as the new representation for my token. So remember, we started with the yellow token. So this is the token that we were interested in. This one tells me how similar is that to others. And now if I take the vector matrix product, in this case, if I take that similarity vector and multiply it with the values of other tokens, what's it going to do is this is going to just give me a weighted sum of these value tokens, and that weighted sum I can represent as the new shape or new incarnation of my the same yellow token. So this is the transformed token after attention. That's how attention works internally. So in a simple sentence, what it does is it looks at others around you, or in this text gen, or like the self-attention, you look at your previous tokens. So basically you are comparing yourself with the previous set of tokens, and based on how similar you are to others, you created a new value for yourself based on the values of others. So together, this computing similarity and then computing this new value, what we are essentially trying to do is to make this token look more like others. So let's look at that projection one more time. So what am I interested in really? So we have this token, let's say this is little, and there are these other tokens. So we had Mary, then we had, then we had token A, and then we also had yourself. So remember, these were the K sides. These were the KA, this is the K had, this is the K Mary, and this is the Q. So we compared, so now we got these similarity scores. So your attention scores are here. So maybe this one is similar 0.5 times, maybe it is similar to here like 0.2 times, maybe this one is 0.3, and then we have now I'm already at 1, so my numbers are incorrect, so let's put this on 0.4, and then maybe this one is 0.1. Now these are my attention scores, and my interest is I want to create a new value for this little. So I want that new value, or the new value of little, to be something like this. I want that to be the 0.4 times the value of Mary plus 0.2 times the value of had plus 0.1 times the value of A plus 0.3 times the value of little. So I want to project a new value for the token little, and I do that by taking the weighted sum, and weights are coming from the similarity scores. So this is what we get in this new projected value. Now there's something we skipped a little bit. So in the slides we said we want to, if you are comparing a token, you want to compare only with yourself and the tokens before you in self-attention. So essentially, if I am comparing this little token here, let's say this is the token that I'm comparing, and I only want to compare with the tokens before it. So how can I do that? The way to do that is to create a mask. This is what we call the attention mask. And this is a little neat trick. So instead of doing any conditionals to say that if this is token I, you only need to compare with tokens I and below that, we create this mask such that for any of the values or any of the tokens before you, you create a 0. And for anything after you, you created a negative infinity. So what it will do is, during softmax, and you do that for all your other tokens as well. So you get this attention mask, which is a triangular matrix. And these negative infinities, when they go through softmax, becomes 0. So what effectively that does is, remember in the weighted sum, at the very end, you are trying to do a weighted sum. So for all the tokens that are coming after you, now your weights have become 0. So essentially you are disregarding tokens after you. And the neat trick was you added a mask, which the mask after softmax created or gave the similarity scores to be 0 for any token that's coming after you. So for example, if we were looking at this token little, remember, and the last token after that was lamb. But now if you are looking at the token little, we should not be looking at lamb. So the similarity score between little and lamb turned out to be, in the attention score, became 0 based on our mask. So when we are trying to create a new value, when we are trying to create a new value for this little, we will, so remember we had all these sums like 0.4 times value of Mary, something like that. So we keep doing that, and at the very end we will multiply 0 times the value of lamb. So we are essentially disregarding any value that is coming for tokens after yourself. So that's the idea of a mask. With that, let's revisit our inference now that we have some understanding. So we were interested in giving a prompt and then generating the tokens, and GPT-2 would work as a function that produces only single token at a time. So we gave the prompt Mary had a little lamb, it gave the first token as eats, and then we appended the token again to prompt and send it through GPT-2 again. We got fleece, and we gave the first step is called the prompt processing, the second step is called the token processing. Another term people usually use is called a prefill phase. So prefilling, the idea of prefilling has something to do with KV cache. We'll come to that in a bit. So there's this prompt processing and then token processing phases, and after that you keep appending and you keep going. Now within the transformer and within attention, how it worked is, you took a token and you created a query token for that one, or you created a different side to it or facet to it, and then you compared your query facet with all the key facets prior to you, and then you got the similarities. Once you have the similarities, you use that as the weights to do a weighted sum over all the values prior to you to create a new representation for yourself. So that's how it worked. Now how do we get this next token? Let's say now we got the first token eats, but what happens when you run it again with the input prompt now being Mary had a little lamb and eats? So how do you get the word fleece? So if you ignore a lot of the details, what happens is, okay, you had this last token was eats. Now we are going to generate the token fleece, and how it will happen is we will again generate 3 Q, K and V tokens for the token eats, and then now we will compare with everything that was before eats. Remember, now this is in the token phase. So all the tokens that were before eats, we need to compare with them. So we had these old key values which are coming from the original prompt, and then this new key value that was generated for the token eats. So we compare the Q with all of those Ks, and then we project a new value. So remember, again we had these old values. Now old values are coming from your tokens in the input prompt, and then we had this new V value that was generated for the token eats. So we take the weighted sum. So now at this point, this is how the attention worked, and if you squint hard enough, ignoring the rest of the pipeline, this is essentially what the transformer will do, and this is what the transformer's pipeline would do. So towards the end, now you would get this word fleece as the next similar token. Now, did you notice something? So during this computation, you are reusing the same or rematerializing the same keys and value tokens that were generated. So there's a little trick that we can do. We don't necessarily need to rematerialize. Instead, this is one of the key techniques how we make inference efficient, is to cache them. So just like how we would do in any other program, where if you are trying to recompute the same thing over and over, why not cache it? So compute the k and v values for anything that you have seen and then keep them. For next time you can reuse them. So that's the idea of this KV cache, and that's why this prompt phase is usually called the pre-filling phase, because during prompt phase what you're doing is you're just filling up a cache. You're filling up your cache with the k and v values for the input for all the input prompt tokens, and after that you keep appending one token at a time for your k and for your k cache and your v cache. So for prompt processing you generate the full QKV caches, and in essence how you get this token, the next token is doing a QKT times v. Ignoring or like squinting so hard, what you are doing is a QKT times v. And then for token processing, what you do is you keep extending your k cache and your v cache with the next tokens k and v values, and then you compare, then you do the same thing, you compare with your q value and then you project a new v value. So this is why you don't need to really have a q cache, because q is, you generate q each time anyway and you're not going to reuse that q, so there's no need to cache q values that you generate. You only need your k and v values to be cached. Alright, so the takeaway of all this is, I mean, this is not going into all the details, but inference predicts the next likely token. But it doesn't necessarily predict the next likely token. What it does is it changes, or it transforms the original token into something else, so that if you were to compare or take a similar token to that transformed token, that similar token is the most likely one to come next. And then attention is the one that enriches this embedding with some information about your previous tokens. So, and then generating multiple tokens is not a single inference step. That's why you have to run multiple steps, and this is why everything becomes expensive. So each step only extends the number of tokens by 1. And if you were to do this naively, you would end up with so much wasteful computations or recomputations, and that's why we can have a KV cache to improve performance of inferencing. Now there are more techniques to improve performance, but this is the essence of how transformers and attention works. And a couple of good resources that I followed while making this video. Shout out to this PicoGPT repository for creating a simple, tiny enough GPT-2 representation that someone can go and read, written using NumPy. So give it a try. And then there's a nice in-detail video from Andrea Karpathy on how to building GPT from scratch. So these two I would highly recommend. I hope you found this useful. Thank you.